Next, let's understand how priority handling can be effectively performed with heaps. Hospitals process thousands of patients daily. Without a smart priority system, a critical heart attack victim might wait behind someone with a minor cut. This is not just inefficient, it's dangerous. The core challenge is simple. How do you always know who needs care first, without sorting everyone every time someone new arrives? This constant resorting is precisely the problem. Every time a new patient arrives, the entire process has to restart, consuming valuable time and computational resources. This is not a sustainable approach for dynamic, real-world systems that need to prioritize effectively. That's where heaps come in. A heap is a tree-shaped data structure that keeps the highest or lowest priority item always at the top, ready to grab instantly. Instead of sorting everything, which is slow, you maintain just enough order to know where the priority item is, which is fast. Think of it like a VIP line at a concert. The most important person is always at the front. You don't sort the entire line by importance. You just ensure the VIP is ahead of everyone else. This fundamental difference is what gives heaps their speed advantage, allowing O of 1 access to critical information compared to O of n for an unsorted list. To achieve this efficiency, heaps follow a strict rule called the max heap property. It states that every parent node must have a priority value greater than or equal to its children. This property ensures that the highest priority item is always guaranteed to be at the very top without needing a full sort. If this property is violated, for instance, if a child's priority becomes 12, which is higher than its parent's 10, the heap is no longer valid. This is an immediate red flag, as the highest priority guarantee is broken. Heaps have mechanisms to quickly restore this property, ensuring data integrity and correct prioritization. Heaps excel at dynamically handling new data. When a new item arrives, like priority 6, it's efficiently placed in its correct priority spot, maintaining the heap property without requiring a complete resort of all items. This makes them ideal for systems with continuous updates, like real-time dashboards or task schedulers. By the end of this video, you'll understand how heaps organize data by priority, why they're faster than sorting everything, and how to build systems that always handle the most important task first. These are the core advantages we've explored. A heap is a complete binary tree with a simple rule. Every parent is either larger or smaller than its children, depending on whether you're using a max heap or a min heap. In a max heap, the largest element is always at the root. In a min heap, the smallest element is always at the root. What makes a heap unique is its foundation as a complete binary tree, meaning all its levels are filled from left to right, ensuring a predictable and compact structure. This property is crucial because it allows us to store the tree's data in a simple, contiguous array, eliminating the need for complex pointers. Heaps don't use pointers like traditional trees. Instead, they're stored in a simple array where parent-child relationships are encoded using index math. This array representation saves memory and improves performance because data is stored contiguously. Let's visualize how a tree structure maps perfectly onto an array and why this encoding is both elegant and efficient. For an element at index I, its parent is at index I-1 divided by 2. Its left child is at index 2i plus 1, and its right child is at 2i plus 2. These simple arithmetic rules allow us to traverse the tree structure without any explicit pointers. This index-based system provides direct access, enabling us to quickly locate an element's parent or children. For instance, to find the parent of the element at index 3, we simply apply the formula. Similarly, to find the children of the element at index 1, we use the corresponding formulas. This demonstrates the bidirectional navigation capability, all through simple integer arithmetic. This visual collapse perfectly illustrates the core concept. A heap is fundamentally a tree in its logic and behavior, but it achieves its efficiency by being stored as a compact, pointer-free array. When we compare this array-based heap to a traditional pointer-based tree, the advantages become clear. The array heap uses contiguous memory, which not only saves space by avoiding pointer overhead, but also significantly improves cache locality. This means related data is stored close together, leading to much faster access and processing speeds. This unified, efficient array representation is why heaps are so powerful for tasks like priority queues and sorting algorithms, offering optimal performance through intelligent memory management. Heaps stay organized to two core operations, insertion and deletion. Let's watch these operations in action and see how heaps maintain their structure dynamically. When you insert a new element, you place it at the end of the array, the bottom right of the tree. Then bubble it up by comparing it with its parent. If the new element has higher priority than its parent in a max heap, you swap them. You repeat this process until the heap property is restored. This is called bubble up, and it takes log n time because the tree height is log n. Now, when you delete the root, the highest priority element, you replace it with the last element in the array. Then bubble it down by comparing it with its children. You swap it with a larger child in a max heap and repeat until the heap property is restored. This is called bubble down, and it also takes log n time. At any moment, dozens or even hundreds of processes may be competing for CPU time. The scheduler's job is simple. Determine what deserves attention right now. A heap makes that decision almost instantly. This ensures critical tasks like handling interrupts execute immediately. The highest priority task is always waiting at the top, ready to be selected. Notice what just happened. As one task finishes, the heap automatically reorganizes itself so the next most important task rises to the top. Dijkstra's shortest path algorithm uses a min heap to always process the nearest unvisited node, making GPS navigation and network routing efficient. Every step focuses on the most promising location discovered so far, avoiding unnecessary exploration. Instead of checking locations randomly, the algorithm continuously asks a single question. Which node can I reach most cheaply right now? The heap answers that question instantly. That's why shortest path algorithms scale to massive road networks, communication systems, and logistics platforms. Huffman coding uses heaps to build optimal compression trees, reducing file sizes for storage and transmission. The heap repeatedly identifies the two least frequent symbols. Without a heap, finding those candidates over and over would become expensive. By always combining the smallest frequencies first, the algorithm gradually builds the most efficient encoding possible. The result is smaller files, faster transfers, and lower storage requirements. Web servers use heaps for load balancing, automatically routing new requests to the least busy machine. Modern applications may receive thousands or millions of requests every minute. Efficient distribution becomes critical. Rather than checking every server each time a request arrives, the system immediately knows which machine has the lightest workload. You can even use two heaps, one min, one max, to find the median of a live data stream in log n time per update. This is useful whenever information arrives continuously, and the answer must stay current. After every new value arrives, the heaps rebalance themselves automatically. The median updates immediately, without sorting the entire dataset again. Financial systems, analytics platforms, monitoring dashboards, and streaming applications all use variations of this idea. Heaps are fundamental because they solve a universal problem. Always knowing the most important thing, instantly, even as priorities change. Different industries call it different things. Priority, urgency, cost, distance, load, frequency. But underneath, they are all ranking problems. And heaps provide a remarkably efficient way to keep those rankings updated as new information arrives. The heap isn't storing everything in perfect order. It stores just enough order to answer the most important question immediately. This efficiency is why heaps are so powerful. They offer O of 1 access to the highest priority item and O of log n for updates, making them incredibly adaptable for dynamic systems. In other words, heaps make prioritization scalable. As the amount of data grows, the cost of maintaining order grows surprisingly slowly. Mastering heaps means mastering priority-driven systems. Understand heaps, and you understand one of the most powerful decision-making tools in computer science.